Hello everyone, welcome to my YouTube channel. Today we will learn about input bias current and input offset current of an operational amplifier. The topics covered in this video are: what is input bias current with bias transistors, input bias current and input offset current, effect of input bias current on source impedance, effect of input bias current on feedback circuits, and finally total output offset voltage with examples. What is input bias current? If you explore the internal circuit of operational amplifier, there are mainly 5 stages and each stage consists of several transistors, and first stage is differential amplifier stage. The transistors in each stage needs proper biasing. As we know, transistor biasing is a process of setting of transistors in initial operating conditions, both in terms of current and voltage, so that input signal can be amplified by them correctly. Whenever the biasing voltages are applied to the op-amp, ideally no current is required for the input terminals. But in practical, some small amount of DC biasing current is required for the transistors in differential amplifier. This current, which is required for the input terminals or differential amplifier, is known as input bias current, represented as IB plus for non-inverting terminal, IB minus for inverting terminal. In case of bipolar transistors are used in op-amp, then it is called base currents of transistors. The input bias current range of an op-amp from some femtoamperes to microamperes. Darlington pair transistors are used to lower the input bias current. Also, to lower the input bias current, MOSFETs or JFETs are used in internal circuit of op-amp. Then these currents which are flowing into input terminals are called as gate currents. The other method to lower this input bias current is by using bias transistors. Means current sources are connected to the bases of both transistors of differential amplifier, so that in theory both these currents gets cancels with each other and we will get very low input bias current flowing into input terminals of op-amp, but not zero. The direction of these bias currents depends upon the type of transistors which are used in internal circuit of op-amp. If PNP transistors are used, then the biasing currents going into outward directions of op-amp. If NPN transistors are used in internal circuit of op-amp, then the biasing currents are entering into the op-amp. The input bias current is defined as the average of these two DC base currents of differential amplifier. That is, input bias current IB is equal to input bias current at non-inverting terminal plus IB plus input current at inverting terminal IB minus divided by 2. In ideal conditions, both currents are equal. That is equal to IB plus is equal to IB minus. But in practical, both currents are unequal. Some difference in biasing currents. This difference is because of mismatch in beta of transistors. For example, if IB plus is equal to 85 microamperes and IB minus is equal to 75 microamperes, then IB is equal to 85 microamperes plus 75 microamperes divided by 2. That comes 80 microamperes as input bias current. The difference in base currents indicates how closely matched transistors are used in op-amp. This difference is defined as input offset current IOS. Input offset current IOS is equal to plus IB minus IB minus. 85 microamperes minus 75 microamperes, that comes plus or minus 10 microamperes as input offset current IOS. The datasheet of an op-amp shows these two parameters. Here the input offset current and input bias current of general purpose operational amplifier LM741 is shown. Every op-amp, even if input bias current is compensated, is going to have some form of input bias current. In most of the applications, this bias current is negligible. But this bias current can be real problem or critical parameter when we are using in precision applications. In general purpose op-amps like LM741 and LM324, input bias current is in the range of nanoamperes. In high-speed op-amps like LT1818 and LT1363, input bias current is in the range of microamperes. In precision op-amps like AD549 and LTC6268, input bias current is in the range of femtoamperes. Now we will discuss the effect of input bias current on source impedance. Let's take an op-amp LM741 and configure it as a non-inverting amplifier. Its input bias current IB is equal to 80 nanoamperes, and we have connected some source into inverting terminal, and source impedance means series resistance of the source is 1 kilo ohm. Assume that input offset voltage is also 0. Then the error in this op-amp because of input bias current 80 nanoamperes flowing through 1 kilo ohm resistor. Then the offset voltage at this point or across this 1 kilo ohm resistor, according to Ohm's law, V is equal to I into R. 1 kilo ohm into 80 nanoamperes, that is equal to 80 microvolts error or input offset voltage going into non-inverting terminal. This error is very small, but in precise applications, this small input offset voltage becomes a real problem because this error will get multiplied with gain and causes real problem. Suppose if our source impedance value is 1 mega ohm, then error you are introducing in op-amp is input bias current 80 nanoamperes flowing through 1 mega ohm resistor, that is equal to 1 mega ohm into 80 nanoamperes, that comes 80 millivolts error or input offset voltage at non-inverting input terminal. So if the source impedance value increases, then our input error will also get increases. So the solution for this is, if you observe IB plus is going into non-inverting terminal, IB minus is going into inverting terminal. So ideally both are equal and opposite currents. These both can cancel with each other. So let's start with a voltage follower configuration. Here our source impedance is 1 kilo ohm is connected to non-inverting terminal. So we will connect a feedback resistor of 1 kilo ohm to its inverting terminal. The value of feedback resistor is same as source impedance resistor, that means 1 kilo ohm resistor. So the error of both inverting and non-inverting terminals are equal. That is, offset voltage across both terminals, that is equal to 1 kilo ohm into 80 nanoamperes, that gives 80 microvolts error. This 80 microvolts error at both input terminals are opposite polarity. Thus they both will get cancels with each other. This is how we can solve the effect of input bias current on source impedance in non-inverting configuration. Now we will discuss the effect of input bias current on feedback circuits. Let's take an LM741 and configure it as an inverting amplifier. IB minus and IB plus are flowing into inverting terminal and non-inverting terminals respectively. Non-inverting terminal is ground potential, so there will not be any effect of IB plus on output voltage, as IB plus is initially 0. But if you observe, inverting terminal is also connected to ground through input resistor Rin. So there will not be any current flows through resistor Rin. All the input currents must come from feedback resistor. And because of this, output voltage Vout is equal to IB minus into RF. So this is the error in output voltage because of input bias current. Let's assume all inputs are 0. Vin is equal to 0 and input offset voltage VIO is also 0. So error in output voltage VOO is equal to IB minus into RF. If RF value is 1 kilo ohm, output offset voltage or error VOO becomes 80 nanoamperes into 1 kilo ohm. That comes plus or minus 80 microvolts error. If RF value is 1 mega ohm, then error or output offset voltage VOO is equal to 80 nanoamperes into 1 mega ohm. That comes plus or minus 80 millivolt. So the error or output offset voltage is proportional to input bias current and feedback resistor RF or gain values. If gain of this inverting amplifier is increased, then error or output offset voltage will also get increased. So to reduce the error or output offset voltage, we must apply equal value of IB plus at non-inverting terminal of this op-amp. The error can be minimized by connecting offset compensation resistor or biasing resistor RB at the non-inverting terminal. The biasing resistor RB value must be equal to the inverse of parallel combination of resistors RF and Rin. If you want to know the derivation of this equation, please check it in the description of this video. So now the error in output or output offset voltage VOO is equal to IB plus minus IB minus into RF. If two biasing current IB plus is equal to IB minus, then error in output will also becomes 0. We can write error in output or output offset voltage is equal to input offset current into feedback resistor value. That means IOS into RF. The formula for the total output offset voltage for the given circuit is output offset voltage VOO is equal to 1 plus RF by Rin into VIO plus IOS into RF. That means non-inverting gain into input offset voltage plus input offset current into feedback resistor RF. The first term represents error or output offset voltage because of input offset voltage VIO. And the second term represents error is because of input offset current or IOS. The derivation of this formula is also shown in description. Please check it there. As we know, it is very hard to predict the polarity of input offset voltage VIO and input offset current IOS. Now let's find out the error or total output offset voltage for the given circuit by using the formula. Here op-amp LM741 is configured as non-inverting amplifier. R1 is equal to 1 kilo ohm, RF is equal to 9 kilo ohm, RB, the biasing resistor, is the inverse of parallel combination of R1 and RF. That gives a value of 900 ohms. The input offset voltage VIO is equal to 5 millivolt. Input offset current is equal to 20 nanoamperes as per the data sheet of LM741. So find out the error in total output voltage. Solution for this is, first we will find out the output voltage without any error. Formula for output voltage Vout is equal to non-inverting gain into Vin. Non-inverting gain is equal to 1 plus RF by Rin into Vin. Let's insert the values in this formula. 1 plus 9 kilo ohm divided by 1 kilo ohm into 50 millivolt. So Vout is equal to 1 plus 9 kilo ohm divided by 1 kilo ohm is equal to 10 into 50 millivolt input. That gives 500 millivolt output. This output if there is no input offset voltage or input bias current, or both VIO and IOS is equal to 0. Now we will calculate the error in output. Error or output offset voltage VOO is equal to gain into input offset voltage plus input offset current IOS into feedback resistor RF. Let's insert the given values in the formula. Output offset voltage is equal to, here gain is 10 and input offset voltage is 5 millivolt. Input offset current is 20 nanoamperes into feedback resistor 9 kilo ohm. That comes 50 millivolts plus 200 microvolt. That is equal to plus or minus 50.2 millivolt error in output. This plus or minus because it is hard to predict the polarity of this error. So our total output offset voltage becomes Vt is equal to 500 millivolt plus or minus 50.2 millivolt. That is either 449.8 millivolt or 550.2 millivolt as total output voltage after the error. That's all about input bias current and input offset current of op-amp and their calculations. So if you have any doubts or suggestions, please mention them in the comment section below. Thanks for watching this video. If you learned from this video, please click the like button. Help others to learn by sharing this video. Please subscribe my YouTube channel and turn on notifications for more such videos. Follow me on my next video, op-amp as inverting amplifier. Have a nice day.